everyone, and welcome to ES405 Lab, which is Measurement, Instrumentation, and Process Control. And you may be wondering why you have to take a course in instrumentation, or even what is instrumentation. And so, my name is Seth Price, and I'll go ahead and get this class started, and maybe by the end of it, you'll understand why you have to know a little bit about instrumentation and why this is important for chemical engineering and for all engineering. And so the course itself, we've got the measurement, the instrumentation, and the process control. And so I put up here making the world quantitative, meaning when you're a little kid, you say this one's bigger than this other one, or this car is faster than another one. But as you get older and advance through your engineering career, it's better to have some numbers to associate with that. In order to do that, we have to take measurements. In order to take measurements, we have to have some sort of instrumentation. So it's the how. How do we take measurements? How do we know something's bigger, faster, more flammable, whatever it is? And then finally, why do we care? A lot of times we have to use these measurements to make some sort of adjustment to an industrial process. And so you'll take a full course on process control, but this is kind of just a little leading edge into that. Why we need to worry about taking a measurement is because we might be using it to make a decision later on. And so you've done some simple instrumentation. I don't know the way chemistry lab at New Mexico Tech is run. I know as a freshman at Virginia Tech, we took a chemistry lab for engineers, and the very first lab, we boiled water. And it was the worst thing stand there and watch the thermometer, and your lab partner would be writing in a book, and every 10 seconds they would say mark, and you would give them the temperature, and then they'd go 9, 8, 7, 6, and then they get all the way down and they get mark, and then you would say it's 32 degrees Celsius or whatever it was. And so simple instrumentation, we're just collecting data. We're not really making any decisions based on it. We're taking manual measurements, and they're at really slow sampling rates. So like I said, once every 10 seconds or so. And we're not controlling a process. When we think about this, how long could we actually do this? Sitting there taking temperature measurements this way every 10 seconds, maybe an hour or two. I get really old. So we're going to talk about what to do about that. So maybe advanced instrumentation, we would have automated measurements, so some sort of computer taking these measurements. So we could do a lot faster sampling rates, and we absolutely have to have some sort of computer measurement to make process control decisions on the computer. So that's kind of the direction we're headed with this. And so a process control loop is simply just measurements plus some sort of a logic we've applied. And then that's basically our process control loop. So basically, often what we do is we're comparing some current conditions, some temperature, some pressure, something to a set point. And if we're not at that set point, we make some adjustment to some other piece to get to that set point. So this could be if our temperature is not high enough, we turn on the heater or keep the heater running until it is high enough. And then once we reach that set point, we turn off the heater, or maybe we're opening a steam valve. So there's lots of ways this process loop can happen. So simple control loop that I know many of you have not seen because you're here at New Mexico Tech, but this is a shower. So when normal people take a shower, they turn on the water and they stick their hand in and say, oh, it's too hot or it's too cold, and they adjust the knob and they stick their hand back in until it's the right temperature. And then they get in and bathe regularly, which is something maybe we should be doing. So that was a simple process control loop. An advanced process control loop, we've got all sorts of different hardware, and it's making these decisions for us. And we're figuring out things like if we have this blue step change here, which of these signals is acceptable? How much can we overshoot? How much can we bounce? And how does all that factor in? So process control class will talk about this in a lot more detail. And there's all sorts of little hardware solutions for that. So that's what is off in the corner. So back to the shower example. A couple more things we can pull from this example. This is pretty much a toy for rich kids and not me, but the LED changes color, based on the temperature. So that's pretty cool. So a couple things that can happen, a couple things that we can pull from the shower example are our sampling rate, and that's basically how often we take a measurement. And there'll be an entire lecture dedicated to sampling rate. Dynamic range is basically what types of measurements can you actually take. So, for example, if the water is too hot, it's just too hot. It doesn't matter. You wouldn't be able to tell if it was 95 degrees Celsius or 300 degrees Celsius just from your hand. It would just feel too hot. So that's going to factor into how we convert a real signal into a digital signal that we will use for automated process control. Also, sometimes how long does it take to respond? So, if you stay in a cheap hotel or something, sometimes you turn the water to hot, and it takes forever to heat up. So that becomes a bigger and bigger issue as you start dealing with bigger and bigger numbers. So maybe in your maybe when you're heating a little 200 milliliter beaker of water, it doesn't take very long to heat it up. But if you start dealing in 10 gallons, 20 gallons, 100 gallons, it's going to take a lot longer. So how fast does it take for changes to take place is an important factor. Also, does our system respond linearly to something we've changed? In other words, can we write it as y equals mx plus b, where we have a slope and a y-intercept? That's going to be important. We like being able to predict how things happen. So if it's not linear, what is it? How close is our measurement to the truth? So I put up here measurement error. So if you were out playing in the snow and then stuck your hands in the water, the water will feel super hot, even if it really isn't. So how much measurement error is there? Also, disturbances and impulses. So I know in our dorm when I was a freshman, if somebody flushed a toilet, the water would all go hot. And so the polite thing to do is you'd yell flush, and everybody would step away from their shower so that they didn't get burned. So how does your system respond to a step change? That's an important feature. So in the end, why we're learning all this, I call this the magic of automation. What's happening is anytime we have some physical phenomenon, be it temperature, pressure, pH, doesn't really matter, we're basically going to convert that into a voltage or a current. And you'll hear this through a transducer. Transducer is just another word for a sensor. And so pressure sensors convert pressure into a voltage or a current. And then once we've received that signal, our computer or our instrumentation hardware will turn around and send a control voltage out to some other device that will convert that signal into some sort of physical change. So maybe we send a control voltage to a solenoid that opens a valve. So that's basically how all of this comes together. And so what's neat about this, and what's maybe a little different about the way I teach instrumentation versus another school or another professor, would be that as it turns out, new sensors are coming out every day. And so the old model of teaching instrumentation involved learning how each specific sensor worked, and how does a thermocouple work, and how does a strain gauge work, and so on. And that there's some benefit to that. I won't go into a lot of detail on that because sensors are becoming more common, different varieties, and becoming cheaper. So where I'm going with all of that is that rather than just teaching you about a couple little pieces, the principle is all the same. We've got some voltage in from a temperature sensor, pressure sensor, whatever it is, and we're sending voltage out for warning lights or motors or switches or valves or whatever on that end. And just as a comparison, uh, back in the back in the 80s, if you wanted to look at, if you're working at Ford and you've cast an engine block, one of the foundries that Ford owns, about the only way you could test it to see if it had any defects was to literally cut it up, and it was a destructive test. So you basically could only use statistics to determine, how many engines were going to be defective, and if there was there was a couple sensors that would be on it, and you had to check engine light. Well, compare that to a modern automobile that has thousands of sensors. It goes through thousands of different tests without destroying the engine. So that's going to be a bigger issue later on in the semester, and I'll talk more about that. So where I'm going with that is sensors have gotten cheap. Actuators, such as motors and such, that we're sending a control signal to, they've also gotten cheaper. So this is something that is just going to become more and more important throughout your career. And also make a quick comment here. There's always some issues. Some folks think in terms of, well, if I automate something, isn't that getting rid of a job, or isn't that putting somebody out of work? Isn't the old way better? So on. Couple points with that. First off, I'll tell you about nitroglycerin production. In the 1800s, when we were first manufacturing nitroglycerin for explosives work, there would be some guy, and he would sit there, and his job was to watch a pressure gauge and a temperature gauge. And if either of them crept a little too high, he would adjust a valve, and if they crept a little too low, he would adjust another valve. And if you can imagine a 12-hour shift like that, sitting there watching two gauges and turning a valve, and factor in maybe that he was hungover from a night at the saloon the night before, often that guy would fall asleep, and more than one nitroglycerin plant exploded because of this. So the 1800 solution was to have a guy sit on a one-legged stool. So he could sit down and watch his gauges, but if he fell asleep or passed out, he would fall off the stool and potentially wake up and could get back to work. So now that's all done remotely. It's all done under computer control. There's no guy turning a valve to adjust these parameters. So it ends up being a lot safer. And so where I'm going with this is any industrial process that you're working on, you're going to have these iterative improvements. So big questions are, how can we make this process more efficient? How can we make this process more accurate? How can we make this process safer? And it's always a cost analysis as to how to deal with these. But once you have an existing process, it's easy to, well, I won't say it's easy, but it's important to be thinking in these terms. And when you go into a new career or whatever, walk into a new plant or take over a new process, these are the types of things you want to be thinking about. And so what I mean by this is, for efficiency, maybe you use less of something, use fewer chemicals, use fewer utilities. How can you minimize unplanned downtime? Are belts breaking? Can you stop the belts from breaking? Can you stop having to clean things out as often, especially when you're not expecting it? So that's using less, generating less, so fewer waste streams, waste heat. Is there any way you can reuse? If you're generating heat somewhere, can you use that somewhere else in the process? In general, you don't like to have stocked inventory. You want to have just, one approach to this is just-in-time manufacturing, where every product you're making is ready just at the time that it needs to be moved out and sold, so that you have no inventory sitting there. In chemical engineering, this is really kind of a big deal, because stocked inventory is just lots and lots of chemical, and often this is flammable or toxic or whatever, and in large quantities. So it'd be much better if you could just produce the right amount at the right time and have it move out. So how can you generate less? Also, how can you make more? So can you uh, get rid of some of your waste streams? Is there a way you can recycle it? Is there a way you can um, sell other byproducts and so on? So those are the types of efficiency things you'll be looking for. For accuracy, how much data can you collect and what do you do with the data? Uh, can you look through historical data and make sure that when you've made some change, it hasn't adversely affected your process? Can you use data to find early warnings for issues or problems that are coming up, or to plan maintenance schedules and so on? So those are important points. For safety, do you have the right machine guards in case? I have a couple of different categories here: physical controls. So, do you have emergency stops and emergency release valves? Do you have redundant systems so that if something fails, you have another safety mechanism? Do you have barriers to keep people from going into the wrong place at the wrong time? Uh, do you have software controls that have historical data, and your data is kept secure so that a competitor or a hacker or somebody can't affect your plant? This one is becoming a bigger and bigger deal with data security. So most of your electronic hardware, a lot of it will have stuff like it'll be passworded. So you have some valve and it's got a password. And if you're the engineer setting that up or the technician setting that up, the temptation is, yeah, I'll just use the default password. And that may be a really bad thing. Suppose that's the valve that controls the cooling water to a nuclear reactor. You don't want to just use the default password, and you want to make sure that all this stuff is secure. So that's becoming a bigger and bigger deal. Once again, I mentioned early warning issues. Is there anything we can find in software that's showing up? Also, there's administrative controls, and that's stuff like standard operating procedures and what needs to be documented and what rules are in place. And so those are all things that you want to be looking at improving as well. So I'll just go through a real quick fictional example here. Maybe you're controlling the temperature in a heat exchanger, and uh, the output temperature, it says the output temperature of the hot side must be below a set point, and you can control the flow rates on the cold side, but nothing else. So maybe in the past, companies just run like a metric butt ton of cold water through it, and that's been good enough. It's kept the temperature down, but you come in on your first day and you're like, man, we're just using a lot of water, and we probably don't need to use all that water. So how could I go about improving this? Well, maybe if the temperature gets close, we turn on the water, and then maybe we have a second set point we set that says basically, if the temperature drops to this set point, we go ahead and scale that valve back. So now that now we know our temperature is going to be between this hot set point and this cold set point, and we're only using that amount of water instead of just tons of water. So maybe we have a little bit of water savings there. Maybe we take the temperature in a couple of places so that instead of just one thermocouple taking one temperature measurement, we have a couple, and we kind of have an average just to make sure that we don't see anything that's standing out. If these three temperatures are pretty close, our average is pretty good, then our average will be pretty good. But if we have something like maybe T3 is reporting a lot higher temperature, we may need to look at that. Was there some sort of hotspot developing here? So that's a way to increase accuracy. Increasing safety. So another thing we could do is, I have up here leak or fault detection. And so maybe we put a flow meter on each side of the cold water flow. And if the flow rates don't match, we can say, hey, there's probably a leak somewhere. We don't know exactly where, but maybe there is. And so then we send an operator, or maybe that looks like a boring job. We probably give it to an intern. And we have the intern walk around warning lights and see if this is a problem. And we just keep iterating. Maybe this is just a tiny part of a big plant, and so this is a a boiler at I believe it's a natural gas, or maybe it's coal-fired. I think it's coal-fired power plant. And, maybe we have our poor intern walk up and down all these steps and check for warning lights. And that they take a long time. And so, maybe there's better ways. So maybe we put some wireless nodes out there, and then we don't have to send somebody walking around in the snow and the hot and everything to deal with this. And these nodes send data back, and it's all processed in a control room. And we just keep integrating and integrating, and we end up with this fully integrated control system that runs something like this big power plant. So, but it all starts here in instrumentation and learning how these different sensors work. And that's what I've got for you today.